Hey everyone, welcome to this explainer. Today we're jumping right into a definitive, really dynamic study guide all about the subatomic blueprints that build our entire physical world. Whether you're aiming to master material science, prepping for a big chemistry exam, or honestly just endlessly curious about what actually makes up the universe, you are definitely in the right place. We're going to completely decode the microscopic architecture of everything around us.
I'm a big fan of structured learning, so here is our visual syllabus for today. We'll be hitting the illusion of solidity, the evolution of atomic models, the subatomic ledger, calculating atomic mass, isotopes and ions, and then we'll wrap it all up with an interactive practice quiz.
All right, let's kick things off with Section 1, the illusion of solidity.
Okay, we need to start by challenging pretty much everything your senses tell you about the physical world. You know, when you knock on a wooden desk or touch the metal of a titanium chassis, your brain is absolutely convinced that you are touching a continuous solid substance. But actually you're not. It's a highly sophisticated architectural ruse. To really grasp this paradox of solidity, let's use a simple analogy comparing the superdense nucleus with the ethereal electron cloud. An atom is roughly 99.9% empty space. The nucleus contains almost all of the mass, but it is incredibly infinitesimal. The electron cloud is what defines the atom's volume, but those electrons possess a totally negligible mass, only about 1/1836th of a proton. Consider this, because it's wild. If you somehow remove that empty electron cloud space from every single atom in the human race, the entire human population's nuclei would literally fit perfectly inside a single sugar cube.
And I love this quote because it brilliantly illustrates why material strategists look at matter not as continuous blocks, but as invisible architecture. The reality we experience every day is just energetic tension stretching across staggering voids. It's this ghostly arrangement. And recognizing this is a total game changer because it shifts us from just passively observing our world to actively engineering it.
So, how did we even discover this ghostly void in the first place? Well, that brings us to Section 2, Evolution of Atomic Models. This timeline is basically a scientific detective story. We start way back in the early 1800s with John Dalton, who proposed that atoms were just tiny, indivisible, solid spheres. Makes sense for the time, right? Then, in 1897, J.J. Thomson discovered the electron and gave us the plum pudding model, basically picturing a sphere of positive dough with negative electrons embedded inside it like pieces of fruit. But that whole idea fell apart when Ernest Rutherford's famous gold foil experiment proved that the atom is overwhelmingly empty space, giving us his nuclear model. Niels Bohr then stepped in to bring some order to that space, proposing fixed circular energy levels for those electrons. Fast forward to 1932, James Chadwick discovered the neutron, finally completing our picture of the nucleus. And today, we operate in the modern era of quantum mechanics, where we know electrons don't just move in fixed circles, but rather exist in these shimmering probability regions called orbitals.
Moving right along, let's jump into Section 3, the subatomic ledger.
Let's zoom right into the actual anatomy of these microscopic wonders and see what's really inside this ledger. Take a look at this diagram of a lithium atom. It's a great visual map. You've got the heavy protons and neutrons locked super tightly together in that central dense nucleus. Meanwhile, those tiny, almost massless electrons are way out there, orbiting in those vast outer shells. It is exactly that massive disparity in size and mass that dictates all the rules of chemistry and physics as we know them.
Honestly, go ahead and screenshot this ledger right now. Knowing these specific properties is absolutely crucial. It's the key to understanding atomic architecture. Protons carry a positive charge, and they literally dictate the element's identity. Neutrons have no charge at all, but they provide the essential mass and stability, which our sources beautifully refer to as the weight of silence. And then you have electrons, with their negative charge and tiny mass, sitting out in the outer shells, fully governing chemical reactivity and bonding.
Which leads us perfectly into Section 4, Calculating Atomic Mass.
The really cool thing here is that we can actually use some very simple math to decode this specific identity of any element on the periodic table. It all starts with the atomic number, which we represent with the letter Z. This is strictly just the number of protons in the nucleus. Think of it as nature's immutable identity card. For instance, a single proton, where Z equals 1, gives us hydrogen, our universal, incredibly abundant fuel. But if nature simply bumps that tally up to 6 protons, Z equals 6, boom, we suddenly have carbon, the highly versatile structural backbone of literally all life.
The other vital piece of the puzzle is the mass number, represented by A, and that is simply the total sum of the heavy particles, so the protons plus the neutrons. When we want to find the missing piece, that weight of silence provided by the neutrons, we just build the concept out logically using these three really simple steps. You identify the mass number, you identify the atomic number, and you just subtract. And this elegantly simple formula illustrates that perfectly. Neutrons equals A minus Z. By subtracting the atomic number right out from the mass number, you figure out exactly how many neutrons are hanging out in an atom. Unlocking this math is what allows engineers and scientists to precisely tune material stability for really high-stakes applications like nuclear physics.
Okay, let's explore some variations in Section 5, isotopes and ions.
So we established that protons define the element, right? But what actually happens when we start tweaking the neutron or electron counts? This comparison here is super important. Isotopes manipulate the weight and stability of the nucleus. They have the exact same number of protons, but an entirely different number of neutrons. For example, standard carbon-12 is totally stable, but if you add 2 neutrons, you get carbon-14, which is an unstable isotope. Its radioactive decay is literally what lets us carbon date ancient artifacts. Ions, on the other hand, manipulate the social life of the atom. Ions are just atoms that have either gained or lost electrons in their outermost shells, which creates a net electrical charge, resulting in positive cations or negative anions.
All right, time to see what we've learned. Welcome to Section 6, Interactive Practice Quiz.
It is time to put this study guide to the absolute test. We've covered the history, the ledger, the math, and the structural variations. So, here is practice question 1. How do you calculate the number of neutrons in a sodium atom where the atomic number Z is 11 and the mass number A is 23? I want you to literally pause the explainer right here, use the formula we just talked about, and lock in your answer before we reveal it. Okay, did you get it? If you subtracted the atomic number 11 from the mass number 23, you perfectly calculated that this sodium atom has exactly 12 neutrons. Spot on. Moving right along to practice question 2. Is an atom that has lost an electron called a cation or an anion, and what is its net electrical charge? Pause the explainer again and really think about what happens to the overall charge when a negatively charged electron is taken away from a neutral atom. Well, because electrons inherently carry a negative charge, losing one means the atom's protons suddenly outnumber its electrons. That leaves the whole atom with a net positive charge, turning it into what we call a cation, like a sodium +1 ion, for example. If it had gained an electron instead, it would be an anion with a negative charge. Last one, practice question 3. How do the hydrogen isotopes, protium, deuterium, and tritium, actually differ from one another? Take a quick pause and try to recall our lesson on that weight of silence within the nucleus and what an isotope fundamentally is. The answer is that they share the completely identical chemical identity of hydrogen, meaning they all have exactly 1 proton, but they differ in their neutron counts. Protium has 0, deuterium has 1, and tritium has 2. Their varying neutronic balances make them incredibly useful for totally different things, ranging all the way from standard industrial baselines to acting as the critical field components for next-generation fusion energy. So, we've journeyed all the way from viewing atoms as solid, unbreakable bricks to understanding them as these incredible, dynamic probability clouds. Having finally decoded the blueprints of the infinitesimal to revolutionize things like medicine, energy, and everyday technology, I want to leave you with this somewhat provocative thought. Now that we're no longer just passive spectators, but actual architects capable of engineering reality itself, what impossible structures will you build now that you hold the subatomic keys to the universe? Thank you so much for joining me in this explainer. Keep asking those big questions, and as always, keep learning.